Okay, should I start?
Yes, go ahead.
Okay, so we're going to shift to something different, and it's the end of the meeting, so I'll try to keep it short. I know you're all kind of tired. And so we were asked to discuss radiation-mediated shocks. Actually, these shocks play a key role in essentially all explosive stellar systems. I will give some examples later on. And in particular, they are responsible for the first electromagnetic signal emitted from these systems. And that includes binary neutron star mergers, to relate it to the last talk. And so I presume that most of the audience here is, just a second, most of the audience here is not familiar with this topic. So what we are going to do, I will give a brief introduction of these shocks. I will quickly explain the mechanism, and then I'll discuss applications. And then Hirotaka will take over and we'll discuss the computational method. He will discuss the method he developed to compute the structure emission from these shocks. And he will show some examples so you can get an idea how the spectra emitted from this shock look like. So that's the plan. So let me start by explaining what are radiation-mediated shocks. So the key feature in these shocks is that the dissipation mechanism is completely radiative. And to be more specific, it is governed by Compton scattering. And essentially, in these shocks, all of the shock energy or the upstream energy in the shock frame is being converted to radiation downstream. So the downstream is radiation dominated. And what's happening is that a fraction of the photon in the immediate downstream, just behind the shock transition layer, as you can see here, propagates backwards toward the upstream. And on the way, it is scattered off the incoming plasma and transfer momentum to this plasma. So thereby it decelerates this plasma. So this is basically the dissipation mechanism. In the non-relativistic case, it's actually diffusive. In the relativistic case, Klein-Shihn and pair production effects will be important. So I'm not going to go to all these details, but Hirotaka will explain a bit more on this. So this is the basic mechanism of these shocks. And one question that one might ask is, what is the photon source? So essentially, there are two regimes. The first time we termed photon-starved shocks. In these photon-starved shocks, the upstream is assumed to be completely cold. So the photons are generated inside the shock transition layer, and mainly by Bremsstrahlung. Not only, but other processes are subdominant. So as the plasma decelerates, photons are being emitted by Bremsstrahlung, and the density and temperature of the photon downstream is determined by the emission rate by these processes. And these shocks are mostly relevant to various kinds of supernovae, maybe low luminosity GRBs in certain models, and also neutron star mergers. The second regime or second type of shocks is what we term photon-rich shocks. In these shocks, the photons are essentially advected by the upstream flow. So the photon production inside the shock is actually subdominant or even negligible. And the photon advected by the upstream flow are compressed and heated, and this is the source of the photon downstream. These kind of shocks are expected in long GRBs, the prompt emission in long GRBs, at least the photospheric component. And in one model, a variation of the shock breakout model for neutron star mergers, it is also assumed that it's photon rich. This model requires actually two shocks. The first one produces the photons, and the second one is this radiation-mediated shocks. I won't go into the detail. So there are some justification for this, but there are, I mean, it's still unclear which one is going to be important for neutron star mergers. Okay, so let's see under which condition in general we expect these type of shocks to form. So as I mentioned, the requirement is that the downstream should be radiation dominated. And that actually means that the radiation pressure is larger than the pressure of the plasma, this condition here. So if you solve the jump conditions subject to this requirement, you can translate this condition into a condition on the shock velocity, which is here given in units of the speed of light. So the shock is going to be radiation dominated if the velocity exceeds roughly 10 to the minus 4 with a very weak dependence on density. And here I normalize density to some typical values expected in stellar explosions. So you see that it's not very restrictive. Essentially, all shocks produced in stellar explosion well satisfy this criterion, so they all should be radiation dominated, mediated. Of course, in order for the downstream to be radiation dominated, the photons needs to be well trapped inside the shock. So that means that the photon diffusion time from the system should be much longer than the shock crossing time of the plasma. So if you equate these two time scales, or if you wish, you can translate this condition into a condition on the optical depth of the system. And the conclusion is that in order for the shock to be radiation mediated, the optical depth has to be larger than 1 over the shock velocity in these units of the speed of light. So for relativistic shock, this is roughly unity. For subrelativistic shock, it's actually larger than unity. And the width of the shock transition is roughly this number, 1 over beta. In the relativistic case, actually this condition is somewhat altered because of Klein-Shiner effects and top reduction, which are going to be important. And you will see some results later on. So the conclusion from this is that fast shocks, namely fast, meaning velocity larger than this value, propagating in a sufficiently optically thick medium, should be radiation mediated. So let me compare this with collisionless shocks because there are some important consequences. So there are essentially two types of astrophysical shock. The RMS I described and collisionless. Now in collisionless shocks, the dissipation is actually governed by collective plasma processes, which are generated by instabilities, collectively called Weibel instabilities. And the typical scale here is the so-called skin depth, or it's the inverse of the plasma frequency. So for typical density, the width of this transition is on the order of, say, a few centimeters or so. And of course, these shocks can only form in optically thin regions if they are fast. And if you compare this to the typical scale of radiation-mediated shocks, you see that this has a width which is larger by many orders of magnitude from collisionless shocks. So for that reason, radiation-mediated shocks cannot accelerate particles. So it's the physics is completely different than collisionless shocks. With some caveats, I mean, subshocks, collisionless subshock may form in this transition, or plasma turbulence may be generated for some reason that I don't have time to go into. But I mean, generally speaking, they don't accelerate particles. Still, they can form a hard spectra by bulk comptonization of the radiation as I described. But these spectra will extend to much lower energies than, say, in typical collisionless shock. So if someone assumes that the shock propagating in an ejector is collisionless, you can get actually honest conclusions. Okay. I will skip this maybe. So let me mention why these are interesting, or what's the application. So as I mentioned at the beginning, the first thing is that in all stellar explosion, essentially, the first electromagnetic signal is produced by these shocks during the breakout process. And I will say a few words about breakout in a minute. And what's interesting is that if you have a good measurement of the spectral evolution, say, and you have a good model to feed the data, you can actually extract important information regarding the explosion mechanism, the properties of the progenitors, etc. So basically, these shocks carry information about the formation of the progenitors. So here are some notable examples. So as I mentioned, shock breakout in various types of supernovae, and here it depends on the progenitor and type of the explosion, what you are going to see. Gamma ray emission from breakout in low luminosity GRBs. At least in certain models, the gamma ray emission in these systems is hypothesized to come from a shock breakout. And essentially, this seems to be consistent with some data on supernovae, but I won't go into this. As I already mentioned, gamma ray emission from neutron star mergers. I'll say a few words about this in a minute. And also subphotospheric emission in long GRBs. So these are a few examples where these shocks actually play a dominant role. So let me say a few words about shock breakout, how this process works. So the key point is that in all of these systems, the shock propagates in a medium of a decreasing density and a decreasing optical depth. And so basically, because of that, the shock is initially optically thick, and the photons are well trapped. So during this phase, it's radiation mediated. And then eventually it reaches some radius at which the photon diffusion time occurs on over a time scale shorter than the shock expansion time, and the emission is released. So this is the shock breakout phase. And actually during the shock breakout phase, the shock undergoes a transition from being radiation mediated into collisionless. But the properties of the emission released, so that will be actually the first signal. So here is a movie of a simulation by Or Gottlieb, done actually in this case, it's in the context of binary neutron star mergers. In this example, the shock is driven by the jet. You see the jet is ejected for about, I don't know, 1 or 2 seconds, I don't remember, and it drives this cocoon described earlier in the previous talk. And so the shock here at the top of the cocoon propagates in this ejecta. It will eventually reach a region where radiation will be released, and probably we are going to see this as a gamma ray signal. Now, this process actually illustrates what's happening in all of these systems. The main difference is that in some of those systems, the medium is static, like in, say, shock breakout from a stellar envelope. In some of them, the medium is moving, like in a breakout from a stellar wind, or in a breakout from a BNS ejecta. So that's the main difference. And finally, before I let Hirotaka take over, let me say a few words about breakout from binary neutron star mergers. So this was very quickly discussed in Udi Nakar's talk. So here, as I showed earlier in the simulation, we think that the shock is driven by the jet ejected post-merger. And at least according to some models, the gamma ray flash observed in GW1708 was actually produced during the breakout of the shock. I mean, the breakout should definitely produce a signal. The question if the signal will be observed and if it's actually dominant or subdominant. So of course, the jet also expected to emit gamma rays. I mean, the gamma ray we see in short GRBs are definitely not coming from shock breakouts, they are producing the jet. What's unclear is what is the properties of the off-axis emission. Actually, we don't really have a good understanding of the gamma ray emission or the prompt emission in GRBs and in these jets. On the other hand, the shock breakout process is actually understood from first principles. But anyway, which one dominates would probably depend on viewing angle and on details. And let me just say in this context that the properties of shock breakout will depend on and also the delay between the gravitational wave emission and the gamma ray flash will depend on the structure and in particular the velocity of the ejector. And in particular, the breakout would probably occur in the high energy tail. And so you really want to get some handle on the density profile. Unfortunately, as already showed, the breakout mass is tiny. It's like 10 to the minus 7 or 10 to the minus 8 or so. So it's unclear if simulation can actually give us this. But I mean, in principle, what you would like to have in order to properly model the emission from this breakout phase is this density profile and velocity profile of the ejector, and particularly at the edge. Okay, so with that, I will stop here and I will now let Hirotaka continue. So I will stop sharing. And
okay, so let me share my screen. Okay. Okay, I guess you're seeing my presentation file. Okay, so let me, maybe, sorry, are you seeing the presentation mode or?
Yes.
Okay, so this is fine, no?
The only problem here is the titles are in Japanese.
Oh, really? Oh, sorry, I don't understand what's happening. Just a minute. Okay, so this one. So now you see. Yes. Okay. Okay. Do you see my mouse cursor?
Yes.
Okay. Good. Okay. Thank you very much. So first of all, I'd like to thank the organizers for giving me an opportunity to give a talk. So okay, from now on, I'll introduce some of the simulation we have done so far on the radiation-mediated shocks. In the simulations, we particularly focused on the shocks with velocities above 10% of the speed of light. At these velocities, the shocks falls out of thermal equilibrium and the simulations becomes important to reveal its properties. Okay, so this slide, okay, this slide is describes our numerical method. And what we do is we use an iterative method to obtain the shock structures. So what we do is first we give a plasma profile given by hand. Typically we impose simple discontinuous shock distribution. And for the given initial profile, we solve the radiation transfer using Monte Carlo method. within the shock profile. And then based on the calculation, we evaluate the deviation from the energy momentum conservations. And from this information, we give a feedback on the plasma profile, and we continue this iterative step until the shock converges to the steady state profile. Okay, this is our method. And the microphysics we take into account is we take into account all the microphysics that is relevant, important in the radiation mediated shocks, that are the Compton scatterings, free emission absorptions, and also the pair production and absorptions. Assumptions here is we assume here pure proton electron plasma in the far upstream, and we assume that all plasma particles behave as a single fluid and has the same temperature. Okay, so okay, so these are the examples of the result of our simulations for shock velocity in the range from 0.1 C up to the Lorentz factor of 20. This is showing the fall velocity, temperature, and the pair density per baryon from upstream to downstream region. So, okay, this is a busy plot, but as you can see, below 0.5 C, there is no pair, but above 0.5 C, there copious amount of pairs appears in the shock. So, okay, once these, so below 0.5 C, there's a rapid increase in the temperature in the downstream region with the shock velocity, but due to the presence of pairs, the temperature downstream is regulated around, say, 100 kV, regardless of the shock velocity. And this is due to the strong dependence of pair density as a function of temperature that serves as a thermostat of the shock. And as a result, the shock temperature in the relativistic regime is regulated around 100 kV. Okay, so also if you look at the shock width as a function of shock velocity, it depends in kind of a non-monotonic manner in the range covering subrelativistic up to highly relativistic regime. Okay, this figure is showing the shock width as a function of shock fall velocity, and as you can see, shock width decreases with velocity in the subrelativistic regime, since the diffusion length is inversely proportional to the shock velocity, as mentioned in the Amir's talk. But once it approaches around 0.5 C, there's a rapid decrease. There's a rapid decrease in the shock width due to the production of copious pairs. So copious pairs strongly enhances the opacity, and this opacity shrinks the physical size of the shock. But above around Lorentz factor of 2, it reaches around minimum, but it again, the shock width again begins to increase with the shock fall velocity in the high relativistic regime. This is due to the effect of crination effect. So reduction of the opacity due to the crination effect dominates over the increase in the opacity in the pair density at this regime. So as a result, you start to see an increase again. Okay, so, and okay, this is a resulting spectrum at the downstream, and as you can see, spectral energy rapidly increase with the shock velocity below 0.5 C, but above 0.5 C, the peak energy is more or less regulated around a few hundred kV due to the regulation of temperature by pairs that I have just mentioned before. And okay, another characteristics in the relativistic shock is that there is a non-thermal high energy extension in the spectrum above the peak energy, and this is produced by the strong bulk componentization that cross the shock transition region and upscattered by the incoming upstream plasma. And the notable feature that is found in all shock velocity is a soft extension of the spectrum below the peak energy. This soft extended tail is much softer than the black body or wing spectrum, which is often naively invoked to model the shock breakouts spectra. This is one of the interesting features found in our simulations. Okay, and but it should be noted, however, that while we can infer the shock breakout signal based on these simulations, the calculation does not take into account the effect of the photon release from the shock that happens during the shock breakout. So this computation does not directly, accurately, precisely predict a shock breakout signal. So to explore this issue, we have also extended the simulation to include the effect of photon escape in our simulation. And these are the examples. So one thing which I should mention is that since our simulation is limited to steady state, it can be applied to model the shock breakout phenomena that happens in the gradual manner. For example, a shock breakout that happens in the wind-like environment, which shows a gradual density decrease with the radius. We can, this simulation can model such as phenomena. Okay, so this is, okay, going back to the simulation result. This is the result. For example, for 0.1 C shock velocity and different color representing the fraction of energy, photon energy that is escaping from the shock. And a notable feature in the subrelativistic regime is that there is a reduction of temperature downstream as a fraction of photon escaping energy increases. This is due to the decrease in the downstream velocity, which elongates the diffusion length, and which in turn result in the enhancement of photon numbers. Photon numbers in the shock that reduce the temperature. And just to show another example for higher velocity in the relativistic regime, this is 0.5 C shock velocity. And as described in the simulations, a previous simulation without escape, pair starts to play an important role in these velocities. And as a result, the pair also regulates the temperature also in this case as well. So the temperature is regulated around 100 kV also in this case, regardless of the escape fraction. And also there is so notable also the one feature I would like to mention is that the presence of subshock as the photon escape fraction increases in this regime. So we found that as the photon starts to leak out from the shock, subshock is formed. And okay, so subshock is a collisionless shock that is mediated by plasma interactions. And we found that this subshock feature, strength of the subshock feature increases as the escape fraction increases. So this implies that once the photons start to escape from the shock, the counter-streaming photons cannot fully stop the incoming plasma, and plasma interaction must play a role in the dissipation process. Okay, so and this is a result for the escaping photon spectrum. And at the subrelativistic shock velocities, as I said, the temperature decreases as the escape fraction increases. So as a result, as the photon luminosity increases, the peak energy shifts towards the lower energies. Hence, on the other hand, in the higher velocity relativistic regime, the temperature is regulated, so the peak temperature is stable at around a few hundred keV. Also, it is confirmed that the soft tail component is a robust feature in the breakout signal, regardless of the shock velocities. Okay, so these are some of our, these were some of the examples, and let me also lastly mention on some of the modifications that is necessary to be applied to binary neutron star merger breakouts. So, okay, this was first pointed out in the review paper by Amir and Udi 2020. But if the mass fraction of the R process element is high, it will enhance the shock running into the R process rich environment. The photon production rate will be enhanced. So this can be understood by this formula. So the free photon production rate can be written using the charge number and the mass number of the element like this. So when the R process element is abundant, it increases the production rate of the photons by an order of magnitude compared to the pure electron proton plasma. So as a result, it reduces the shock temperature, and this figure shows the analytic estimate for the downstream temperature as a function of shock velocity together with the points obtained from our simulation that takes into account this enhanced photon production rate effect. So, and from the as you can see, we found a good agreement. The numericals, we found a good agreement with the analytical estimate and our numerical simulations. And as you can see, the temperature, comparing the temperature from the pure electron proton plasma case, when the R process element is abundant, roughly factor of 10, you can find a around factor of 10 difference, factor of 10 reduction in the downstream region when the R process element is abundant. So this result indicates that for our given velocity, shock velocity, peak energy of the shock breakout energy will be lower by a factor of 10 in the R process rich environment case. And also the shock velocity at which the pair production becomes important turns out to be higher So according to our result, per production becomes significant around 0.7 C, which also shows agreement with analytical estimates. Okay, so this is a final slide. Sorry, I took too much time, I guess, but okay. This slide writes down some of the topics, open questions that may be discussed in these sessions. So so far, as Amir mentioned, so radiation. Oh, sorry, can. Do you see my screen now? Sorry.
We see your the screen background,
Background. Okay.
a bunch of file icons.
Okay. Sorry. What?
There it is.
Okay. Good. Okay. Good. Oh.
Yeah.
Okay. So, yeah. As already mentioned, so radiation mediation shocks can be a possible origin of gamma ray emission in the binary neutron star merger. I mean, like the RB70A like event can be produced by shock breakouts. But then the one question is that at which viewing angle the radiation mediation shock, the shock breakout will dominate over the ordinary, normal prompt GRBs that is produced at the same time from the relativistic shock. And I also like to mention on some of the aspects that are not well understood. I'm not sure how well the magnetization of the merger ejector is constrained, but if the sigma parameter in the ejector exceeds few percent, strong subshock can be formed even before the breakout. So in that case, it will give rise to a very high temperature in the shock, and it can, so it can change the signal and some of the properties of shock as well. Also, once the subshock is formed, some level of particle acceleration is expected, and it can affect the properties such as breakout signals and such things. And I also would like to discuss on the possibility that which the radiation mediation shock may have on the kilonova emissions. So actually, we have explored on the effect of photo disintegration that may play a role in the shock running into the R-process-rich environment due to the presence of non-thermal photons in the radiation mediated shocks. So I mean, so high energy photons can be produced in the radiation mediated shocks, and it may we expected that may result in the photo disintegrations, but according to our estimates, numerical result, we found that effect is negligible. So I'd like to discuss on whether there are any other possibilities that the shock may have on the composition of the ejector. For example, if the strong subshock will be present that I have just mentioned, it may lead to the presence of high energy photons that again may give rise to the photo disintegration, which was found to be ineffective in the non-magnetized case.
Yeah, we'd like to leave some time for questions.
Okay, sorry, that's all. Okay. Yes.
Nandit?
Yes.
Yes, please go ahead, Nandita.
Hello.
Yes.
Hello.
Yeah, am I audible to you?
Yes.
Yeah. So first of all, I would like to say that I'm very new to this field and I'm learning something new every day from this workshop. So thank you so very much. Also, please excuse me if my question is very naive to the level of this workshop. I would like to ask, does the viscous dynamical ejecta of neutron star mergers has any kind of correlation with the other parameters which we use to study the mergers of binary star system? For example, I have this paper where I've worked on the correlation between coronal mass ejections and the sunspots. So do we see any such correlation here between dynamical ejecta and the parameters?
Sorry, I may not understand your question. You are asking about the correlation between the dynamical ejecta and what parameters are?
Any other parameters which we basically use to study the binary mergers?
Yeah. Do you mean, for example, the masses of the neutron stars going in?
Okay.
Okay. Sorry, I may not be the right person to answer this
Yeah,
question.
actually, I'm sorry, my question is not directly related to your presentation specifically, but in general context, because I've seen like few of the presentations where they have specifically talk about dynamical ejecta. So that's why I thought to ask this question, if there is any kind of correlation between dynamical ejecta and any other parameters that we use to study the binary system.
Sorry, maybe someone else can answer this question.
Yes, I think there have been a number of mentions in earlier talks about, in fact, how the mass of both the rapid and the slower ejecta depends on the mass of the neutron stars and their mass ratio.
Okay, thank you so much. Thank you.
As well as the equational state.
Yes.
But yes,
Yes.
it depends on a number of parameters.
Yeah, which is not really a parameter, it's an unknown bit of physics.
Okay, thank you.
And see?
Hi, Amir, and thank you very much for this nice talks. Can you go back to your to the slide in which you described the profile on the temperature profile of it's one of the first slides in which you're describing the temperature profile of the I think it is number 10, yeah.
Okay.
No, not number 10, 11, number 11.
Okay.
The next one, okay. Yeah. Yes. I'm puzzled here. You have in the Newtonian cases, you have the usual situation. I'm talking about the temperature. The temperature of the downstream is higher than the temperature of the upstream. But when you go to the relativistic situation, the situation is inverted, and the temperature of the upstream is much higher than the temperature of the downstream. Can you explain this phenomena?
Yeah, it's okay. You can understand it as the penetration of photons up towards the upstream. So as the so the downstream temperature is regulated around MEC square in the relativistic case, and incoming plasma is relativistic, and this Kleinian effect is so significant, and it penetrates a very large distance. So this produces a large precursor rise in the temperature, and yeah. So and and the plasma tries to reach the Compton equilibrium, and it's and as a result it becomes very high temperature. So,
but I mean, it's mainly due to purple. You can see that it drops when pairs are pair density increases exponentially. So what's happening is the temperature is large, but the energy carried by these thermal particles is really negligible. But once you start producing pairs, you share the energy among many more particles. So, the mean energy drops.
Yeah.
Just because you produce a lot of pairs and photons.
Yeah. The fundamental pressure has to increase.
Yes.
Right. And that's carried by all the pairs. I actually have a question about the opposite limit. In the smaller beta and higher density cases, the temperature is in the kilovolt range. Now, particularly when, in general, but also particularly when we have a lot of high Z elements, as you'd expect from our process, there are plenty of bound electrons on those nuclei at kilovolt temperatures.
Okay.
And so I would expect that the opacity would be considerably greater than what you'd get from Compton scattering and free alone.
Okay, but the typical temperature is like, okay, typical temperature is.
Yeah, in that same plot that C pointed to. I guess it's
Okay,
slide
yeah.
11.
It's
I do-
figure 11.
Right. And these temperatures are often, I mean,
Yeah,
kilovolt range even post-shock and colder than that pre-shock.
It's a very good point indeed, and it's not taken into account here. So it's mainly relevant for fast shocks, but not relativistic or mildly relativistic.
Yeah, once
And,
you go
I mean-
to beta of a few tenths or less,
Yes,
you
and
have to worry about it.
this is an excellent point to think about.
And that would be, and you then have much greater optical depth.
Yes. Not only much greater optical depth, it can actually also alter the, I guess, it can also alter the emission rate and the shock profile itself. So yeah, this is something, yeah.
Yeah, and if it's really, kilovolt and it's solar abundances, then you're probably just over the edge where the free electrons are the dominant issue. But for enriched heavy elements or for slightly lower temperatures, then the atomic features are probably going to be pretty important.
yeah, I see. Yes.
Depending on how heavy are the elements, I mean, this can be interesting also up to 10 keV or even slightly
Right.
higher.
If there's a lot of if there are a lot of our process elements, and they have atomic numbers of 50, 75, and so on, all those binding energies are many keV.
And this effect will be important all the way to
hundreds of kilovolts in some cases.
yeah, hundreds of kilovolts. Yeah.
And this is a regime in which there's probably a specialized community who have thought about it a lot.
Right. But I guess that you also will excite, free electrons that are still pretty energetic. They will excite these atoms. So you have some emission processes that are
right.
not bremsstrahlung. Yeah. So yes,
absolutely. Yeah.
That's
right. Emission and absorption are corollaries in inverse processes, and
yes,
essentially, what this will do is take you closer to thermodynamic equilibrium. How close you get is going to depend on parameters and so on, but it always moves in that direction.
well, that if it's important up to 100 keV, it means that you may not produce pairs actually. If your temperature will be lower, I mean, because of this abundance of heavy elements, it probably will affect the pair production. Yeah, okay, that's something.
That just in the last couple of days, I've been thinking about a different kind of shock situation, which I realized from your talk is radiation mediated, but is at these lower temperatures. A timing coincidence.
Right. It's a very good point.
Are there more questions? Kaya.
Hi, thank you, Amir and Anita, for the good talk. I wanted to ask, I think this might be quite a basic question, but specifically in mildly relativistic cases, why would the single fluid approximation or assumption be appropriate?
Okay, maybe I should answer this.
Yeah.
Thank you.
So that depends. In subrelativistic shocks, if you have no positrons, and let's suppose you have only one ion species for simplicity, then it's easy to show that, you know, the radiation force will induce a very tiny charge separation that will produce electrostatic field in the shock transition layer, and this will couple the ions. In the relativistic case, this is not possible because you have positively charged positrons. So what happens there is that if the shock is unmagnetized, is that you will produce, you know, a large relative drift between the species, and that will actually produce plasma turbulence. And we have a very recent paper out showing a 2D peak simulation of this process. And indeed, we find this plasma turbulence to dominate the coupling of the species. Now, if the shock is magnetized, then it depends on the level of magnetization. There is a critical magnetization above which the pairs become magnetized, and then you actually have a very good coupling. So we are now studying this critical magnetization, and the impression is that in certain systems, the magnetization will be sufficiently high to actually couple the species. In other systems, it will not be sufficient. So you will produce this plasma turbulence. And then it's very interesting because this plasma turbulence might actually accelerate particles by second order Fermi or something. And it can actually completely change the structure, particularly during breakout, structure of the shock and maybe the properties of the emission. So this is something which is now under study by, in a collaboration with the Princeton and Stanford groups, and mainly using plasma simulations. So it's a non-trivial problem. I mean, in the non-relativistic case, it's simple, but if you have more than one ion species with different charge to mass ratio, it's the same thing. You are likely still to have, because you cannot couple the different ion species. If they have different charge to mass ratio, then you will inevitably produce, I guess, plasma turbulence. So this is also something we're studying. So I mean, the final word is not out yet. We have to understand exactly what you're asking, how this coupling occurs. So I had one slide which I actually skipped on this. I thought it's to this, not since you asked.
Okay, thank you.
I forgot to say that we should really thank Ito for giving this talk at a completely unreasonable hour. Yes, you're in Japan now, right?
Yeah, it's
so it is 1 a.m. or 2 a.m. by now.
2 a.m. now.
2 a.m., yeah.
So for 2 a.m., this was the best talk that I heard at 2 a.m. in the morning.
Thank you.
Thank you.
Yes, you're right. We should be especially grateful. And any more questions or comments? Okay, well then, thank you, Amir and Hirotaka, for presenting the subject so thoroughly.